Welcome to this final Q&A session. Just a reminder that May 25th is the last day of the course, and the course material will still be available till end of August, and you can look at the material at your own pace. The videos will be made public on YouTube, so you can even look at those on YouTube, and the files associated with it are on GitHub. Those will be accessible too. If you have any questions, you can ask me. I'll be here for 30 minutes or so, and you can unmute yourself and ask me questions. Or if you want me to go over any of the notebooks or course material that we have discussed so far in the course, I can do that as well. You can unmute yourself and ask me questions, or you can type your questions in the chat. Either of them is fine with me. Yes, you can go ahead and type the question in there. Unmute yourself and ask me a question. The question is, can you go through the architecture of MLP model once? I mean, the output you get when you run the model. You could be any model. So the question, more specifically, it's MPNN readout and then parameters. For example, output of this. Okay, so let's just go with the simplest one first. So let's try with neural networks, and let's try this model first. Okay. So we have the model, just this. So let me quickly run these cells so that we have some data. I can show you what's happening. And if others have any questions, do feel free to type a question in the chat. I can come to your question when I'm done with this, can answer your question when I'm doing this as well. Let's see, it's installing. And let me import the libraries. Featureizer. I hope I have fraction one. I import, split the data set, use the data loaders, collate function, load the data. I also get the valid and test loaded on. And here we have the model. So I don't know whether it's specific to this or not. So let me mention what's happening here. So in some cases where we train a custom model, I think, where we do, let me even pull that code up. So I think this question was a bit related to this one in specific. Where is that? Modifying neural network code, pre-trained models. I should have pulled this one anyway, but oof. Let's look at both of those. So at one place, what we do is we have the class of MPNN model, and these are the inputs required to create the model. It'll tell us how many, for example, how many nodes you want as output, how many hidden layers there are in a model, and how many steps to perform. So this will build the model architecture. So what you can do is you can specify each of them, like end task equal to 1, num step message pass equal to 6, or you can create a dictionary over here, in which the keys are the argument names that you need and the argument values. So that is what we end up doing in here. So when we load this parameter.json, it's a dictionary. And when we have the dictionary, we use these keyword arguments. And that's where we can put in the parameters that we need as the model input. So we can do that even in this case. And if you have a dictionary, so if I want to do it for this, I would create a dictionary. So params equals, and what all we need is in feats is 100, and hidden feats is 512. And whatever is left over will be by default set somewhere. So end task is 1. So I can put in this as a dictionary. So the code could be something like, I won't execute it, but if someone is confused with that code, model equal to MLP predictor, and then instead of typing all of this, what I would do is that, and then PARAMS. So this is this parameters, and let's see what happens now. Okay, so let me execute this model somewhere else and show you what difference we get in that. So code, we have this, and then model. I did not run that. Oh, no, my bad. So we have this. End task. Make sure all the names are right. End task is end task. And then we have this one here. So by default, dropout is already set to 0 and it's already 0 over here. So default values are taken for parameters which are not set, and other parameters already taken by what input you give it to them. So there is a follow-up question. Hidden feeds is the length of hidden layer, right? So yes. So hidden features is the length of the neurons in one layer. So how many neurons do you need in one layer? So that depends on this feature. If you want more number of layers, you would need to add more layers. So linear layer, a value layer. So there is one linear layer, and that linear layer has a value layer that forms your one hidden layer kind of thing. And if you want to add more layers to it, you need to add layers over here. And that's what we talk about in customizing ML models, where we add more layers. And within that layer, we need to decide how many features we need. And that depends on the number of neurons that we put in here. And that's hidden features. And all models will depend on some or the other parameters. For instance, if you look at this MPNN model, let's see. So there are edge nodes, hidden features. So these are edge hidden features. So it's specific to this model that you're using. So if you look at the edge hidden feature, is just used in MPNN GNN model. So if you want to look at what it's doing over here, I would look at the code for MPNN GNN and see how that model creates these layers. And if you want to add more layers, you can add more layers in it. Going back to the neural network that we have here, once we set how many neurons we need and how many the layers are decided by the model itself. So sometimes you can change it, but in this case we have one linear layer followed by a value layer and batch normalization. So let me again explain what a dropout layer does. A dropout is a way to avoid overfitting of something. And let me see whether I can get that thing and show you what is actually happening. Let's go to neural networks. So this is the neural network model architecture, and let's use a pen here. So these are the inputs, these are the neurons, and let's say we requested what 500. Oops, this is hard to write. 512 layer, 512 neurons in this one. Okay, so in this layer we requested 512. What happens sometimes is you have, let's draw epoch, and I'll just say epoch on this side, and this is loss. So loss on that axis. As you proceed in training, you should have your training loss going down somewhat like that. Let's say this is your training loss, and you have your validation loss. And in this, you see that it's just like this. The loss is the difference between the validation loss and the test loss is large. That means your model is overfitting to the data. And one way to reduce overfitting is to avoid a lot of neurons in the layer. So what you end up doing is you say, okay, I don't want 512 neurons. While training, you randomly shut off some of the neurons. So that's what dropout is doing. So a dropout of 0 means all neurons are active. A dropout of 1 means all neurons are inactive. And a drop off of 0.5 means half of the neurons will be active in training. Randomly, the neurons will be selected and they'll be turned off. For instance, during one, say let's say during one training batch, you have the first neuron over here not active. So there's no information being passed to this neuron. All the information is just being passed to the second neuron. And what that does is the weights of those are not overfitting to something. And that helps in minimizing this error that you see in the validation and training loss. And that's what uh, the dropout does. It shuts off some of the neurons so that you don't overfit the data. Okay. So then the question would be, what happens if we set the hidden layers as half of it instead of using a dropout of 0.5 or something like that. So what happens in that case is your model sometimes may be underfitting and it still needs neurons. What we are trying to do over here is, when we have a dropout of 0.5, for instance, we are shutting off some of the neurons randomly. So in first epoch, maybe the first neuron is turned off. In the second epoch, maybe the second neuron is turned off, but the first neuron is still working. So the weights are the ones that are not overfitting to it. And that's what is changing. You still have, if you put in a x value, input value for prediction, all the neurons, 512 neurons will be there and the data will pass through all 512 neurons. But during training, the weights of those neurons were not overfitted, if that makes sense. So we are just avoiding the overfitting. But if you half the hidden feature size, the prediction will still use the half size for prediction. But if you use dropout of 0.5, you'll still have the 512 neurons when you make prediction. But only while training, some of those are randomly turned off in each epoch so that the weights are not over optimized. Okay, I hope that answers the question. So there's another question, I think, in day one exercise, while the splitting data with FastML did not allow for validation dataset. Is that possible? I'm not sure what did not allow for validation dataset. It depends on, I think, how many, it should usually split it up. I'm not sure what happened while splitting the data. The data with FastML didn't allow for valid dataset. I don't, there should be some error in the code, I think. But I would suggest give it a try again and let me know. I'm still here. And see, just restart the notebook and try to split it. If it doesn't work, let me know. We still have time. Okay. So let's go back to the code here. So we have that, and we have batch normalization layer. Batch normalization is, let me go back to the thing here. So here we have a hidden layer. So hidden layer is going to output something into this neuron, next neuron. And we have a activation function, which is value function. And then we have some linear layer, which which does the linear stuff. And what happens here is, okay, so you have some value and that needs to be put into this. If the value is large, okay, so if this one gets maybe say 10,000, what is this? Yeah, 10,000. The output of this is 10,000, and all the other values are between 0 and 1. So all the other values of them. So let's say this one is 0.2, and maybe this neuron gets an input that is again 0.5. All of them between 0 and 1, but one of them just overshot. A large deviation. So what happens over here is sometimes only this neuron may be active because these values are close to 0, and this is a large value. So your model may not be right again, and it will try to overfit. There'll be a lot of error between the validation and training. And some of those values may not be well normalized. So what the batch norm layer does is it takes all the input values and tries to create a normal distribution of them instead of having a discrete type of distribution, and tries to keep all the values between 0. I think no. It tries to have, it can't work here, but yeah. So it tries to have a mean of 0 and a standard deviation of 1. That's how you get a normal distribution. So it transforms all those values. Though this output at 10,000, it'll try to change the value a little bit so that it fits this distribution, and in that case allows training to be a little bit smoother. And even if all values are close to 0, if you remember, we need to take the gradient, and that's how we update the weights. And if these values are close to 0, the gradient doesn't train well. So the updates to the gradient are very slow. And let's see whether I can get that part here. Where am I? Okay, yeah. So let's see. Oh, yeah. So you need to calculate the gradients. And what happens is if the values are so small, the gradients itself will become very small. And that means the model update, so the update of the weight is again small. So that slows down your training process. Though you may run for 100 epochs, the training is very, very, very slow. And because the way the gradients end up being so small. And this is called vanishing gradient problem in machine learning. And that's the reason we use a little bit different activation functions and other things in ways to avoid this. And batch normalization is one way in which we make sure that the output is not very different or not too small. We just try to make it a normal distribution, and that is what the batch norm layer does. I hope that answers that question. This is the batch normalization layer. So once you have this, what is happening in the model right here is you have your x's that are x values. So x values come to this linear layer, and linear layer is W1 x1 plus W2 x2 plus W3 x3 and so on. And W1, W2, W3 are the weights that you want to optimize. And the hidden features, the linear feature that you're giving it is ones and zeros in this case, because we are using fingerprint over here. So once we pass that, it passes to the linear layer, and there's an activation on top of it. If there's a dropout, this dropout only acts during training, and during testing, when we say model.eval, we'll see that in the code later on. But when we use model.eval, this is no longer valid, and batch normalization changes the way it moves the data. While training, it knows how to shift it, and it tries to use that knowledge of how to shift it uh, in the validation. But in training, these two act differently. And when you have the linear layer, it goes to the linear, and the output from the linear passes to the value. And again, batch normalization, so that the outputs are a linear, have a normal distribution, and then passes to the other linear layer, which then outputs one value, which is what we requested here. And bias is whether we want the uh, additional b parameter that we have at the end. And it's, if you look at the equation of a straight line, it's y is equal to mx plus c. The c is the bias. So or you can say you don't want bias parameter, you can ignore it, but if you want to add it, you can add it. So does this answer the question, what happens during model training? Okay. So there's another question. Any recommendation of GNN books or courses? I think I forgot to add that thing about GNN model. So it's called Distill. So this is the link. I can share this link. And this is where you have more interactive thing from Google, and they show you what it actually looks like, the edges, the vertices or the nodes, and what happens with the features. But what we concentrated on this course is mostly on how to use the info, how to use data and train them, and not concentrate a lot on depth of the math and other things that is going on behind this. And the application here is for chemistry, and that's the reason I wanted the course to be more focused on chemistry, and we have the data, how do we train it, and not go on to graphs and other things. So this is pretty interactive site. You can see how to what is an adjacency matrix, which we didn't go a lot in this course, but we just assume that we have a molecule that is a graph. Let's see, a molecule with a graph, and how do we do the predictions, and what happens in training for these models, but not at the at what is the math that's going on behind it. But this is a pretty good website, and I do think they have some references at the end. You can go through it. But what I usually recommend if someone wants to look into these is go to some of the libraries that you want to use. Deep Graph Library, the DGL, is one of them, and you'll find a lot of papers, and you'll see how it's done. DGL Life Science or any of those. So if you go to this DGL Life Science on GitHub, you'll see a lot of papers on how people have done that. So there are examples. So you can even look at examples, list of examples here. So there you go. So you can look at any of these, and there's a paper, there's GitHub associated with it, and property prediction with all different models. We did some of them. We did the neural network MPNN model, but you can look at the other codes and see how it's done. We only looked at regression and some classification. There's another class of generative models which generates molecules given a property, and I initially thought that this is something good to include, but it'll be a little bit difficult to understand given the time that we have for this course. But I would strongly recommend looking at all of these type of things that you can do. So there's another question. DGL is the right place. I want to see how it is implemented. It depends on what your task is. DGL graph, if you're playing with graphs, yes, it looks pretty good for playing with graphs and featureizing as graphs. There's also another one which is DIG, I think, DIG, and this is one of the models that mm, this is one of the library that is also good in let's see, for graphs. It's called Dive into Graphs. They also have something similar for graph generation. There's something how to generate a graph, supervised or self-supervised learning. This is explain graphs. So this is something people are trying to do now, is how to get explanations for these predictions. What it predicted a value, and you want to now know the reason why it predicted the value. You want to know what chemistry is behind with the prediction. So these are some things that people have been trying to do, and this is still ongoing field of research. It's not still there yet, but you have ways to do ways to understand what's happening. And then you have 3D models and prediction with accuracy scores. So all of these libraries usually have some of the other ways to tell you how to go about with it, but all of them have a different way of coding. So if you look at the code for this, it'll be a little bit hard to understand, but what we have covered in this course is the basics, and you may see how the basics apply to this little bit sophisticated thing, because they are trying to generalize everything so that you're not only implementing one model with that thing, you'll be implementing 10 or 20 models. So they need to modify the codes to make the 20 models work with the same code, and that's why it gets a little bit complicated. But you will see how it actually works with them. The other one is DeepChem, which we have been using throughout this course. DeepChem has a lot of tutorials you can look at, and data splitting more tutorials. There's also model training. So let me just show you how complicated it gets with some of these models. So we have a PyTorch model. Let's look at PyTorch model. The PyTorch model is you make the data set, a NumPy data set, and we discussed this somewhere in data set splitting, how we do data set splitting. We have PyTorch model. They will create a model with a linear layer, 10H activation, and another linear layer. They just pass it over here. Model is this. Loss is model.fit. And it's going to run for 5 epochs. The code looks pretty simple, but if you look at the execution of it is a little bit complicated when you do all of this. So if you want to look at what is the code behind this, you can click on the source code on anything. It'll take you to the source code, and here you see you have the torch model, and this is some parameters. We have the init function, and it needs a model, regularization, optimization, learning weights. But after that, it gets a little bit complicated, and sometimes you'll see that device is none if something you set CUDA over here. This is how you do training a little bit, and then you have weights and biases. But you'll see important things in here, which is they do all of this. But when we look at training, model.fit, you had to provide a data set and do all of that. The code over here again is complicated. Look at it. So it just self.fit generator, self.default generator. But all that boils down to is the training loop over here. So all of that is just done to make sure the data is there. And then you have a model loop, the loop that we use for training. And with this loop, you generate a batch, and they are using something called prepare batch to get input labels and weights or something. That's what we did too. From the batch we get inputs, the x values and y values, and then optimizer dot gradient 0, make sure that gradients are zeroed, and then you make model and then pass in the inputs. It'll give you outputs, and once you have those, calculate the loss function. And there is the loss function. Once you calculate the loss, you propagate the loss backward and then update the weights. And this part is getting the average loss for each batch. Though the code looks complicated throughout, it's essentially doing what we just did in few lines of code. Because they want to generalize it in most cases, it ends up being complicated. But if you are thoroughly understanding what we did in this course so far, you'll be able to see how more complicated codes work. And DeepCam, DGL, uh, dive dive into graphs, all of these are pretty good libraries, and I would suggest going into DeepChem first, because it's for everything. So you can see docking, you can see meta learning, hyperparameters, and this is pretty good for starting point. But the reason I didn't take a lot from here is the code is just so complicated at the end, because it tries to generalize it. But once you have some idea of how to train a model, I would strongly recommend looking at these codes and see how you can use them. I hope that helps. So there's another question, which is there a library to convert CASID to smiles? There may be something like Pubchem, which may do it. So if you look for Popcam Python, they usually end up having something like that, where you give in CASID and then you get smiles. You may download it somewhere if possible in a CSV file or something, and then use it. Put in all the IDs and make sure you get the smiles from somewhere. But you can do some searching on that. I haven't used something like that before. I usually end up starting with smiles and then proceeding further with the study. So were you able to split the model again? Was there a problem in splitting the model? Splitting the data, sorry, with FastML. Before splitting out, you need to make sure that before splitting, you need to make sure that the data is clean. If the data is not clean, it becomes a little bit difficult to split it. But if there are null values, make sure you drop them before splitting and then split it. But with FastML, I don't think there should be any problem splitting it, because all the code that I've looked at so far should work for splitting. Okay. Any more questions? If there are no questions, I would like to thank you all for participating in this course. And the wrap-up part of this course will be made available in few minutes or so, and you can download. You'll get a certificate of completion, which can be shared on LinkedIn. And for that, you can just take the post survey and get the certificate. And there are some instructions on how to get the certificate once you complete the post course survey. And do keep in touch with Chemistry with Code for more events like these, courses or workshops. you can connect to Chemistry with Code on YouTube channel of Chemistry with Code, and on Facebook page. You can find the links on the course website. I'll put those links in there. There's another question. Can you give a brief intro to on libraries we imported? Slightly confusing because we use scikit-learn for test split as well. Yeah, so scikit-learn is a pretty good module for uh, training and test split, but the problem is it does not give us a validation split. So we can't split it into three. I don't know whether they have implemented that before or not, but what we need is you can usually have just two splits, train and test, like 80%, 20%, or 70-30 or something like that. But if you're using deep learning methods like artificial neural networks or something, you need to have another split, because we are doing hyperparameter tuning. And in hyperparameter tuning, you're training the model and looking at the validation data set, and then making sure that the hyperparameters you choose are fitting well for the validation data set. So that's the reason you need another data set that the model has not seen at all to make your testing predictions. And there's no need for even using any of the splitters, any of the FastML or scikit-learn or any of them. You can just split data by using pandas itself. So you can say pandas dot sample, take a sample. Maybe that's what we have been doing in. Let's show you. So that's what we have been doing in some of these models over here, where we say we take a fraction of it. Where was it? Oh yeah. So this gives us 10% of the data set. So you can say, I want 60% of the data set. You get one data set, and then make sure that from the original data set, subtract this part of the data set, and from there you select another 10% or so. So there are multiple ways of splitting it. There's no need of absolutely using one library to split it. But if you need to split it based on molecular weight or more chemistry specific type of splitting, you would need to use featureizers that are available in DeepChem or somewhere to make sure you split it according to that target that you have of splitting, and not just random splitting of data. So even you can use, if you want to use scikit-learn, you can use scikit-learn and use the test and train split. But you can use something like 80 for training, 20 for test data set, and again split the test data set into 50-50, so that you end up with a validation and another test data set. So even that can be done. Splitting is dependent on how you want to split. There's no specific way of splitting. The reason I used this library FastML is it splits into all of these, and it uses a data set, a data frame to do it. And that's what we use for loading of the data. That's the reason I use this, and not complicate stuff with using scikit-learn, splitting it twice, making more complicated stuff in there. But it's all left to you on what you want to do. Do we get LinkedIn certificate for this course? Yes, there's a LinkedIn shareable certificate for this course. Once you complete the survey, the LinkedIn certificate will be available, and the links to the survey would be available pretty soon, in maybe 10-20 minutes or so. Okay, if there are no further questions, again, I would like to thank you for participating in this course, and I hope you learned some basics and will be helpful in applying to your research or exploring more applications for chemistry with ML. Thank you. Have a great day, great night. See ya.